Well, good evening. Welcome to Space Oddities. Sorry if you experienced a couple of stutters there. We had a couple of technical problems there, but not to worry. We can put those behind us. Hope you are well. Welcome to our Tuesday live stream. I'm joined this evening by Daz and Roger and Lou. Michael is with us in spirit, if not totally in body, because he's still feeling unwell, but he has joined us for this evening. So you're not feeling 100% then, Michael? You can't hear us. Never mind. So anyway, tonight, what have we got for you tonight? Well, tonight we're going to be looking into a very strange thing in the universe that's been discovered over the last few decades, this mysterious force that is moving thousands of galaxies towards one point in space. And we're going to be telling you all about that. But to do that, we want to back up a little bit and tell you about a few more things that we need to tell you before diving into that to set the background, if you like. So we'll be doing that a little later. So hope everybody's had a fantastic week. Thank you for joining us. If you are joining us for the first time, because we did have quite a few new viewers last week. So if you are joining us for the second time, you are most welcome. And there we are. Let's just do the normal housekeeping bits before we go any further. And if you want to support the channel, you can do so in a bewildering variety of ways. You can buy us a coffee, and this QR link, if you want to scan it, will take you to the buy me a coffee page. And you can also click the link that's just appeared in the chat. You can also support us by going to the Space Oddities shop and buying yourself a Space Oddities t-shirt or hoodie. Great stuff, great quality stuff. And you can also make a donation directly to Space Oddities by clicking the super chat icon, which is the one under the chat window with the $ written on it, and that will allow you to donate to us directly. If you value what we do, if you want to keep us producing science instead of nonsense, and we know that there's an awful lot of nonsense floating around the internet at the moment, especially about Comet 3i Atlas, as we were discussing last week, then if you support what we do and trying to bring you the science rather than the nonsense every week, then your support is gratefully appreciated. There are thousands of AI-generated inverted commas science channels out there delivering AI slop and nonsense and lies and misinformation. But what we do on Space Oddities, we give you the facts, we give you the science, we tell you how things are rather than how some AI thinks they should be. So that's what we do. You can also join our Patreon. We have a Patreon page, and you can find that at patreon.com/Space Oddities. For just a few pounds every week, you get access to lots of stuff that we produce, our videos, the presentations that we deliver for you on Tuesdays, and a lot of other stuff. And just for a few pounds every month. And all of that money, all of your donations, however you want to do it, supports us and helps us keep the channel going and pay our bills. So we're very, very grateful for your support, because we would like to keep doing this for you. And we hope that you would like us to as well. If you don't, put it in the chat. Simple as that. So there we are. So that's the housekeeping out of the way. Just to give you a heads up about what's happening tomorrow on Space Oddities. We had big success with that feature we did about the science behind Comet 3i Atlas last week. So we're going to give you another chance to see it. So we've edited the section about the comet from last week into its own video. That will be premiering on YouTube on the channel at 8 p.m. UK tomorrow. And it will be live. In other words, there will be a chat window there where you can interact with us, ask your questions, and post your comments. So that's 8 p.m. UK on the channel tomorrow. It should already be there on the channel. So just go along at 8 o'clock and join us, and we can watch the video together. You've probably already seen it, but if you haven't seen it, then you might want to have a look at it, because we did, as I said, delve into the science behind this incredible interstellar comet, rather than the absolute tsunami of nonsense that's sweeping social media and YouTube. And it's getting even more bizarre every week. Anybody seen any really bizarre ones this week? I've seen a few.
What about the
comet?
Oh, there's just absolutely hundreds of things on YouTube and all that, and you know it's all misinformation.
Yeah.
And of course, the sad thing about it is that you've got some well-known astrophysicists who are also beating the drum for this malarkey. We're talking about Avi Loeb.
Yeah.
And it just seems very strange that these people, it's isn't there a little Japanese chap? I can't think of his name now.
Michio Kaku, yes.
Yeah, he's another one. These people are well known in the astronomical community,
Mm.
and they're well respected. But then they come up and start this nonsense. It's very sad, but yeah, there's a
Well,
lot going on, right?
I sort of expect it from Michio Kaku because he is a renowned self-publicist who doesn't miss. He's not a bit of one. He's a huge media tart, and he doesn't miss any opportunity to promote himself, even if he's talking nonsense. But Avi Loeb, as we were saying last week, renowned astrophysicist with a glowing career behind him. But the last few years, he seems to have gone a bit David Icke and talking absolute nonsense. So there we are. Sandra says it's all for clicks and views. Yes, it is. It is, but not in Avi Loeb's case. I mean, to be fair to Avi Loeb, the paper that started all the controversy that he started, he concluded in the paper that there was a 40% chance that the comet was an alien spacecraft. So because it's not something we can rule out entirely, he's quite welcome to put a percentage on it, although you may think 40% is too high. But the internet picked up on that immediately as it's an alien spacecraft. And he thought, oh, this is getting lots of coverage. I'll better say some more. So the stuff he's coming out with now is just absolutely ludicrous. Anyway, enough about the comet. Let's move on. And let's go to the news for this week. So just give me a second to set up the news. And we will have a look at the news for this week. There's quite a bit in the news this week. Just give me 1 second to get to the right place. Here we are. So this is the news for the 21st of October 2025. First item, scientists have discovered a supermassive black hole in an unexpected location. Now, let me ask the team here, where would you not expect to find a supermassive black hole?
In my shed?
In your shed, possibly.
Floating unanchored in space?
Yeah, basically, you wouldn't expect to find a supermassive black hole very far from the center of its host galaxy, but that is exactly where they found one. And what they found was a tidal disruption event, or TDE. That's where a black hole eats a star. This one has the delightful name, predictably, of AT2024 TVD. And this passing star was torn apart by the black hole's immense gravity. Now, this resulting outburst produced one of the strongest and fastest radio flares ever recorded. What makes this remarkable is the black hole's position. And it's far away from the center, 2,600 light years from the galactic core. Now, this off-center placement challenges the long-held belief that supermassive black holes always reside at the hearts of galaxies. So this galaxy does not appear to have been involved in a merger of any sort, which might have shifted the position of the supermassive black hole. What the hell is it doing 2,600 light years away from the center? Well, there's a suggestion that it could be due to a past galactic merger that we're not seeing the evidence of. Or some sort of gravitational interaction causing it to drift through space with remnants of its original system. But this is really interesting because we've never seen a supermassive black hole that's not at the center of a galaxy.
May I ask you a question, Andy? This is fascinating, as all of your reporting is. What kind of galaxy is it, far away from? Is it an elliptical, a spiral?
No, this is a spiral galaxy.
Wow. Then I have no idea. Carry on.
No, I think I'll need to confirm that, but from memory, it's a spiral galaxy. So this does force astronomers to rethink, the co-evolution of galaxies and their central black holes. And, it does imply that there may be more undetected. So, relics of sort of ancient collisions and some sort of cosmic upheaval that could reshape our understanding of galactic dynamics. So this is really interesting find. And of course, I'm sure astronomers will be on the lookout for more. There was news that our galaxy has got a wave running through it. Now, this comes from data from ESA's Gaia mission. It's a vast wave rippling through the Milky Way disk, hope you can see it in that animation, starting near the galactic center and extending tens of thousands of light years outwards. The phenomenon affects stars between roughly 30,000 and 65,000 light years from the center, with some stars found above and others below the galactic plane. Their vertical motions show a coordinated wave-like pattern, clear evidence of a large-scale oscillation sweeping through the galaxy. Now, the origin of this ripple remains uncertain, but one leading theory suggests it was triggered by a past encounter or merger with a smaller satellite galaxy, such as the Sagittarius dwarf galaxy. Such an impact could have gravitationally disturbed the Milky Way's disk, sending oscillations through its stellar population that still persist today. Future Gaia data releases are expected to refine these measurements, though, helping scientists determine how often such galactic seismic events occur and what they reveal about the Milky Way's structure, evolution, and gravitational environment. So this was completely unexpected, this massive wave running through the Milky Way, which, if it wasn't the result of some sort of merger or capture of a dwarf galaxy, it's difficult to see where it came from. So that's a really interesting finding.
Just a quick question, Andy, from Ian.
Yeah.
I don't know whether to take this seriously or not.
Go on.
Do we have to hold our hands up when it reaches us?
No. Right, next question. Okay. So moving on, Murchison Wide Field Array, or MWA in Western Australia, it's a low frequency radio telescope. It operates at roughly 70 to 300 megahertz, composed of thousands of small antennas spread across a remote radio quiet site in Western Australia. This is going to be subsumed into the square kilometre array eventually. It's got a very large field of view, and it's very sensitive, making it ideal for mapping the early universe. Now, they've used 9 years of data from the NWA to generate the most detailed radio map yet of the early universe, and this is it. They focused on that elusive 21 centimeter radio signal emitted by neutral hydrogen during the so-called dark ages and early reionization era. They didn't detect the signal outright. They established the tightest constraints so far on its strength and behavior. The findings suggest that the intergalactic gas was already being warmed by the first black holes and stars. This rules out scenarios in which the gas remained extremely cold until reionization. So this marks a major step forward in probing the universe's infancy, setting the stage for next generation instruments like the Square Kilometre Array to finally detect the 21 centimeter hydrogen signal directly and unlock the details of cosmic dawn. Now, cosmic dawn is that period in the early universe when there was the maximum amount of galaxy and star formation going on. And we've never been able to detect the signal from that directly. But now they put a lot of constraints on what it should look like. So this is great. And of course, once the Square Kilometre Array comes online in just a few years, then almost certainly it will be found, because that radio telescope is going to be 1,000 times more sensitive than any radio telescope ever built. And that's coming online around 2028, 2029, the first section of it anyway. Okay, moving on then. What have we got next? Well, this is all about a gamma ray burst. It's the longest lasting gamma ray burst ever recorded, lasting roughly 7 hours. Typical gamma ray bursts last mere seconds to minutes. So this is a major anomaly. What makes this unusual isn't just its duration, however. Its characteristics of hard spectrum, rapid variability, high energy output points to a central engine of a stellar mass black hole driving ultra relativistic jets. After evaluating and ruling out a range of standard progenitor models that you get for GRBs, magnetar flares, typical collapsars, or active galactic nuclei events, the researchers have proposed a helium merger scenario. Now, this is where a black hole merges into the helium core of a companion massive star, forming an accretion disk and powering prolonged jets that emit gamma rays over extraordinary durations, in this case, 7 hours. This challenges the conventional classification of GRBs and suggests there may be a rare subclass produced by black hole star mergers, opening fresh avenues for understanding stellar evolution, jet mechanics, and extreme high energy astrophysics. So the more we look at gamma ray bursts, and these are the biggest blasts in the universe, putting out incomprehensible amounts of energy, the more we realize that there's not just one type, there's a whole spectrum of them, and each has a slightly different origin. But to find one that lasts 7 hours instead of seconds to minutes is an amazing find. And there you are. That's the explanation. This new type with a black hole merging into the helium core of a companion massive star. So a new animal in the cosmic zoo, if you like. So there we are. Okay, sad news really. This week NASA have confirmed that the International Space Station is scheduled for retirement. They're going to start the retirement process in 2030 and full decommissioning by early 2031. And it's had a continuous human presence for decades, involves 15 countries, and has served as the premier microgravity laboratory. The retirement decision reflects the age of the space station, high operating costs, and the matured state of its infrastructure. It's basically starting to fall apart in small ways. Now, rather than simply end human access to low Earth orbit, the move signals a strategic shift by NASA. They're going to transition from owning an operating station to becoming one of many customers in a new marketplace of privately owned commercial orbital platforms. These commercial destinations are intended to pick up the research, habitation, and technology development rules that the ISS has played. In the process of retirement, the ISS will undergo a controlled deorbit to ensure safe re-entry over a remote ocean area. While the era of this renowned orbital outpost comes to a close, the next chapter begins with commercial space stations taking humanity's low Earth orbit presence forward. And there are a number of different companies who are building space stations that will replace the ISS and hopefully do the same amount of brilliant scientific work. The aim of which is to truly understand what effects long-term spaceflight has on the physiology of the human body. So we will, of course, be sad to see the ISS go, but it is showing its age. It is getting more and more expensive to maintain, and that's it really. All good things must come to an end, I suppose.
Andy, can I say something about that?
Of course you can.
I just want to say that, so with the deorbit and whatever, what about commercial companies? I think like Axiom, they were going to send their modules up to the station, dock the station first. Is that right?
Yes, that's right. That's right.
Will that still happen? Do you know, or is that?
As far as I know, it's still happening. And
right.
And in case you don't know, viewers, the Axiom, who've already mounted a few missions to the International Space Station, they are building a space station attached to the International Space Station, which will then detach and become its own space station.
Yeah.
And they've got 5 years to do it. So as far as I know, that's still going ahead. I haven't heard anything to the.
No, I haven't heard anything from Axiom for some time now. No.
Okay, so now this is hang on one second. There we are. This is an interesting picture. let me explain what you're looking at. This is an Einstein ring. You can see the Einstein ring there. This is a gravitationally lensed image of a galaxy about 10 billion light years away. But if you look where I've put the arrow, there's a dark object in the Einstein ring, and astronomers believe this is a clump of dark matter. The object's mass is estimated around 1 million times that of the sun. So this is about 100 times smaller than any previously detected lensing mass of this type. Again, they've used the Event Horizon telescope to have a look at this, and they've detected a subtle distortion in the arc of this ring, and this can only be explained by an intervening mass. Because the object shows no visible stars or light, the most plausible explanation is a dark matter clump rather than something like a dwarf galaxy. And this discovery does support the cold dark matter theory, which predicts that dark matter forms small, sort of low energy clumps that gradually grow. The ability to detect such invisible masses opens a new method for probing the distribution and nature of dark matter in the universe, and suggests that many more of these elusive clumps may eventually be discovered. So that's really interesting because, as it says, you know, it's difficult to explain this dark mass any other way than by the fact that it's a clump of dark matter, because it's not emitting any light, and it's completely dark. There's no EM radiation coming from it as far as we can tell. So it's really, really interesting that this could be a clump of dark matter. Obviously, confirmation on that needed. Okay, moving on. This is a young star called HOPS 315, about 1,300 light years away. This is an artist's impression. Well, not an artist's impression, should I say. This is a composite image from several radio telescopes. It's a direct glimpse of the earliest phase of planet formation around this young star. And this is using the combined power of the James Webb and the Atacama Large Millimeter Submillimeter Array, otherwise known as ALMA. They detected crystalline silicate minerals and silicon monoxide gas beginning to condense in the star's surrounding disk of gas and dust. These first solid materials are forming in a region analogous to the asteroid belt in our own solar system, inside roughly 2.2 astronomical units from the star. The detection marks a critical milestone. Scientists now have real observational evidence of the very first steps in the construction of rocky planets, rather than inferring the process indirectly. Now, because HOPS 315 is very young, and it is oriented favorably for observation, it offers a rare sort of live look at a system at the dawn of its life. This helps bridge the gap between theoretical models of planet formation and actual data, providing fresh insight into how Earth-like worlds may emerge elsewhere in the galaxy. So absolutely incredible that we're seeing a planetary system forming this early in the history of the planetary system of HOPS 315. So really interesting stuff. So slowly but surely we're getting to know more about the very early stages in the formation of planets and the minerals and gas and everything else they need to form in the protoplanetary disk. So really, really interesting stuff. Okay, moving on. Astronomers have detected an enormous bridge of neutral hydrogen gas stretching around 185,000 light years between two dwarf galaxies, NGC 4532 and DDO 137, about 53 million light years away. Alongside this bridge, they also found a massive gas tail extending about 1.6 million light years, and this is the longest such structure observed to date. The analysis suggests that this structure formed due to the strong tidal forces between these two dwarf galaxies and the influence of their movement through the hot, dense gaseous environment of the nearby Virgo cluster. The ram pressure experienced as the galaxies plunged through this medium appears to have stripped gas from them, stretching it out to form the bridge and tail. Now, because neutral hydrogen is the basic material for star formation, this discovery offers a powerful new insight into how galaxies interact, lose or redistribute gas, and change over time, particularly when they are in a dense cluster. So absolutely amazing to see this bridge, this massive bridge and tail of hydrogen gas. And we're going to learn a lot about how galaxies evolve from this and how they interact. So that's another fascinating one this week. And astronomers have discovered what may be the most chemically pristine star ever observed, located near the edge of the Milky Way, about 85,000 light years away. This star has the wonderful name, as ever, as SDSS J0715-7334. It's a red giant star, but it has an astonishingly low level of heavy metals. Metals in astronomy means basically anything heavier than hydrogen, helium, and lithium. And it has an iron abundance more than 10 times lower than any previously known star of this type. Uniquely, its carbon concentration is also exceptionally low, a characteristic that sets it apart from the other ultra-metal poor stars, which often have elevated carbon levels, not exceptionally low ones. This strongly suggests it could be a direct descendant of the universe's first generation of stars formed from nearly pristine material. The motion of this star indicates it might have originated in the halo of the Large Magellanic Cloud before being accreted into the Milky Way. Its existence challenges current models of star formation, which predict a minimum heavy element threshold for low mass stars to form. And this opens a new observational window into the early universe, allowing scientists to study the chemical fingerprints left behind by the first stars and refine our understanding of how the cosmos evolved from simple to complex. So again, quite an amazing find, this sort of pristine star that may well be directly descended from the first generation of stars. And a lot more work needed to be done there. But if so, it's an ideal laboratory for testing our theories of stellar evolution.
Andy, sorry, did you say what mass this was?
Did I say what mass this was? No, I didn't.
No, that'd be interesting to find out as well.
Yeah, we don't have the mass for that, unfortunately.
Yeah, because if it's vacant if it's devoid of all the metals, as you say, the element, then this could be a very massive star.
Yeah,
because as you get more and more elements produced as the stars die, it actually cools the gas, which prohibits it from forming ultra large stars. I'll tell you what, just stay tuned, people, because I'll be talking about population 3 stars hopefully later in the program. So just stay tuned. This is what we were talking about last week. So that's very interesting. That's
and perhaps you could just at the moment ask ChatGPT or something what the mass of that star is.
You'll have to give me the number.
Yeah. Okay. Right. Well, when we finish this,
you finish off, and then if you put it in the chat,
we'll have a look. Okay, so very interesting stuff indeed. So now, coming to the last story for this evening, does the name Chiron mean anything to you? Chiron, not Sharon.
I was going to say it's the moon of Pluto, isn't it?
No, that's Sharon. This is Chiron. Chiron.
Well, rings a bell.
Anything about Chiron?
Is there something to do with Lord of the Rings?
Discovered in 1977. It's a centaur. Now, centaurs are really interesting objects because they're neither asteroid nor comet, but they've got the features of both. They're sort of a hybrid between comets and asteroids. And they've been observing this on and off since 1977. And they've known for years that it was surrounded by material of some sort. Well, shock horror, in the new research, scientists have obtained their best data using a telescope in Brazil to go along with data from 2011, 2018, and 2022. And there was a huge surprise. Recent observations have revealed that Chiron is surrounded by rings. It has a 4-ring system with 3 inner rings at roughly 273 kilometers, 325 kilometers, and 438 kilometers from the center of Chiron, respectively, and a much more distant 4th ring at about 1,400 kilometers. These rings appear to be evolving in real time. Now, Chiron is about 125 miles or 200 kilometers across, and it's got the rings are that diameter, and they orbit Chiron once every 50 years. This is really surprising because ring structures were previously thought to be limited to large planets. Obviously, this discovery offers a rare opportunity to study how ring systems form and change around smaller bodies. And it does challenge these traditional views of small body dynamics and provides insight into how icy and rocky remnants in the outer solar system may interact, shed material, and indeed reorganize into ring-like structures. So we've never seen a body like this with its own ring system before. Considering it's quite small, it's quite amazing, really, when you think about it.
Ring system.
So there we are. So that's the news for this evening.
Excellent. Thanks for that, Andy.
If you have any questions, viewers, obviously put them in the chat.
So those observations that established the rings around Chiron, those must have been stellar occultation observations.
Yes.
Is that right?
I think, yes, I believe so. It's difficult to see how you do it otherwise, but absolutely amazing that these small bodies can form rings. So that's a new one. Yes, another new animal in the cosmic view, a centaur, which is a cross between a comet and an asteroid, forming rings. Every week there's something totally new, and that's what makes astronomy such a wonderful thing to be involved with, as I'm sure you will all agree. Every week there's something new and fascinating and weird and wonderful. So there we are. Okay. So that's the news for this week. There'll be more next week, I'm sure. There won't be an Einstein of the week this week, viewers. I haven't seen anything worth including in Einstein of the week. Piles of nonsense, as I said earlier, but none of that is really worth including, because I don't find it funny anymore. I find it depressing. So nothing really amusing to go in Einstein of the week this week, but I'm sure we'll be back next week. So let's move on then to our main feature for this evening. Now, what we're going to do, first of all, to set the scene, we're going to give you 2 presentations, one from Daz and one from Roger. And then I will be telling you all about this weird thing that is pulling thousands of galaxies towards it out in space. So to kick off this evening, we need to start with the basics of the structure of the universe and then move up to more complicated things in the universe. So Daz is going to be telling us about the cosmic web. Roger's then going to tell us about clusters and superclusters. And then I will tell you all about this mysterious thing that is pulling thousands of galaxies, our own included. So I'll hand you over to Daz, who's going to tell us about the cosmic web.
Okay. Just give me a second. Right, here we go. Can everyone see that?
Yeah, that's fine.
Oh, that's brilliant. Okay, then the cosmic web. And basically, I mean, you just got to look at the actual name, and it does what it says on the tin, to be quite honest. What we'll be doing is unraveling the largest structure in the universe, a magnificent tapestry of dark matter, galaxies, and cosmic voids that stretch across billions of light years. Universal architecture. The universe is architecture. For the most of cosmic history, the universe's true structure remained invisible to us. We could see individual galaxies scattered across the night sky, but we couldn't perceive the intricate pattern connecting them. The cosmic web represents the largest scale structure in the universe, a sprawling network of galaxy filaments, clusters, and vast voids that shapes everything we observe. So what were the early hints of this web? The 1980s revolution. 1981, we had the first glimpses. Robert Kishner and colleagues discovered the Bootes void, a massive empty region 330 million light years across, hinting at cosmic structure. 1986, the Great Wall. Valerie de Lamparent, Margaret Geller, and John Hirschkruer mapped galaxies in slices, revealing sheet-like structures and enormous voids. 1989, the Center of Astrophysics Redshift Survey provides the first comprehensive three-dimensional map showing the web-like distribution. The web wasn't built, it actually evolved from the subtle density fluctuations in the early universe, which were created in the expansion. The gravity wove an intricate cosmic tapestry over 13 billion years. This computer simulation, shows how the universe's large-scale structure formed over billions of years. The animation begins shortly after the Big Bang, when matter was spread almost evenly. As time passes, gravity pulls dark matter and gas together, creating thin glowing filaments that stretch across the simulation box. These filaments meet in bright nodes, the locations of massive galaxies, clusters, and superclusters. The result looks like a three-dimensional cosmic web slowly emerging from chaos, revealing how galaxies become organized into vast networks to be observed today. So what's the cosmic web's architecture? Well, basically, if you think of a spider's web, you won't go far wrong, except it's three-dimensional. So what does it made up of? First of all, you have the filaments. These are the vast chains of galaxies and dark matter stretching hundreds of millions of light years, forming the web skeleton, sorry. Nodes, this is where all these filaments join. Nodes contain dense galaxy clusters. These where filaments intersect, containing thousands of galaxies bound by immense gravity. We have voids, enormous empty regions containing few galaxies, occupying most of the universe's volume, and you'll be seeing some figures on this later. Sheets, flattened walls of galaxies forming the boundaries between neighboring cosmic voids. So how did the web form? As we said, it was quantum fluctuations, tiny density variations in the infant universe, imprinted during cosmic inflation. Dark matter dominance. Dark matter's gravity amplified these fluctuations, creating the scaffolding for future formation. Gravitational collapse. Matter flowed along dark matter filaments, forming the first galaxies at intersection points, so that's at the nodes. And continuous evolution. The web continues growing with filaments elongating and clusters merging across cosmic time. Mapping the invisible. Using the galaxy's redshift surveys, measuring how light stretches as galaxies move away from each other. Astronomers construct three-dimensional maps revealing the web structure. The Sloan Digital Sky Survey mapped over 3 million galaxies. Gravitational lensing. Massive structures bend light from distant objects, allowing us to map dark matter distribution directly. This technique reveals the invisible scaffolding of the cosmic web. And computer simulations, of course, AI. Powerful supercomputers model billions of years of cosmic evolution, reproducing the web's intricate pattern and testing our theoretical understandings, just like the simulation we just watched the video. Right, numbers behind the web. 500 million light years. That is the length of the longest known filament, the Hercules Corona Borealis Great Wall. And as we said about the voids, empty space, 80% empty space. Volume of the universe occupied by cosmic voids. 10,000 galaxies. Number within the largest galaxy clusters at filament intersections. The intergalactic medium, the Webb's hidden component. Between galaxies lies a diffuse plasma, the warm, hot intergalactic medium called WIM. This tenuous gas, heated to millions of degrees, contains roughly half the ordinary matter in the universe. Detecting the WIM proved extraordinarily challenging. It emits faint X-rays and absorbs specific ultraviolet wavelengths from distant quasars, revealing the cosmic web's gaseous skeleton. Dark matter forms the Webb's invisible skeleton. Comprising 80% of all matter, dark matter's gravity orchestrates the cosmic dance. Galaxies are merely tracers. Galaxies are merely tracers, lighting up the vast dark framework, but truly defines the Webb. Current research frontiers. Early Webb formation. The James Webb Space Telescope observes the universe's first billion years, revealing when the cosmic web began taking shape. Dark matter distribution. The Euclid mission maps billions of galaxies to trace dark matter across cosmic time with unprecedented precision. And hidden gas filaments. New radio telescopes detect neutral hydrogen in filaments, revealing gas flows between the galaxies across the Webb. So here we have a couple of the assets that we were just talking about. You've got the James Webb Telescope revealing the very early cosmic web, and Euclid mapping the dark matter in the cosmic web. Why the cosmic web matters. Galaxy evolution. The galaxy position in the web, whether in a dense cluster or isolated void, fundamentally shapes the development, star formation rate, and ultimate fate. Cosmological tests. The web structure provides crucial tests of our cosmological models, constraining dark energy, dark matter properties, and the universe's evolution. Matter cycling. Filaments channel gas between galaxies, recycling matter and fueling ongoing star formation across cosmic time. Future observations. Next generation surveys. The Vera Rubin Observatory will photograph the entire visible sky every few nights, tracking how the Webb evolves in real time. Multi-messenger astronomy, combining observations across the electromagnetic spectrum with gravitational waves, will reveal the Webb's most violent events. AI-enhanced analysis. Machine learning algorithms will identify subtle patterns in massive data sets, uncovering new insights into the cosmic structure. And this is how the Vera C. Rubin will look like. In fact, it looks very much like that now. So, and it will be going first light very soon, if it hasn't already. Maybe Andy can answer that one for us later. The Webb and our place in it. So our Milky Way resides within the local sheet, a flattened structure near the edge of the local void. We're flowing along a filament towards the Virgo galaxy at 600 kilometers per second. Oh, it's messing up my hair. It's blowing me hair. Understanding the cosmic web helps us comprehend our cosmic address and the invisible forces shaping our galaxy's journey through space and time. Key takeaways. A universal pattern. The cosmic web represents the largest structure in the universe, formed by dark matter's gravity acting on quantum fluctuations from the Big Bang. Recent discoveries, though theorized earlier, the web's existence was only confirmed through galaxy surveys beginning in the 1980s, revolutioning our cosmic understanding. And active research, current missions are mapping the web in unprecedented detail, testing fundamental physics and revealing how galaxies form and evolve within the cosmic scaffolding. Now, if you were, it's hard to imagine this cosmic web. So, what do you think it would actually look like if we could see it, and even better if we could fly through it? So, let's just have a look at this simulation while I just conclude with a quick recap of what we were just talking about. So, here we are. The cosmic web is the large-scale structure of the universe, a vast network of filaments clusters stretching across space. These filaments are made mostly of dark matter, which provides the invisible scaffolding that holds everything together, along with thin gas and countless galaxies strung along their lengths like pearls on a thread. Where several filaments meet, huge clusters of galaxies form, while the spaces between them, called voids, are almost empty. In this NASA it's an animation, the galaxy clusters are shown as bright dots over billions of years. Gravity pulled matter into this web-like pattern after the Big Bang, revealing the grand design of how the universe is organized. So if you're just watching this animation, you can watch it all day as if we were flying through the cosmic web, as if we could see it. So thank you very much.
Thanks, Daz. That's great. It's interesting that without invoking the idea of dark matter, it's difficult to see how the cosmic web formed. I'm just putting that out there because, as far as I know, MOND, the modified Newtonian dynamics, the, if you like, alternative to dark matter, doesn't have any explanation for how the cosmic web formed. It's only if you invoke dark matter that forming this sort of invisible scaffolding, if you like, on which these filaments and later the galaxies grew, that that you can explain it. I wonder if Lou's got any thoughts on that.
Well, you're right about that. Notice I've been avoiding a debate with you on MOND.
We must have that debate. We're going to.
But there are weaknesses in the dark matter model as well, and it may be that a hybrid model might work, or maybe something completely out of the ordinary. But you're right, you need something with at least the theoretical gravitational power of dark matter to form the structures in the universe that we see today. Yes.
Yeah. Interesting. I don't suppose we're going to get an answer to all that in the near future, but it's.
Oh, I don't know. What's so fascinating is I tell my my undergraduate class at the beginning of each semester that the universe is going to be very different by the end of the semester, because we are learning so many new things about it. As you were saying, I think earlier, Andy, every week new findings.
Yeah.
So I wouldn't put a peg in that quite yet.
Well, I always use the oft quoted figure that what we know about the universe is doubling every 10 years, and that rate is accelerating. And with the new generation of instruments coming online, the Vera Rubin, the square kilometer array, Euclid's data coming in, a lot of the extremely large telescope. I mean, over the next decade, there will be an avalanche of new data. So perhaps we will finally get the answers to some of these fundamental questions.
kind of a Moore's law for the universe, I see. Right?
Yeah, absolutely. So we will see.
We
So-
had a comment earlier. I have to go back here. Something about a non-zero curvature of the universe in deep space.
Yeah.
Is that Paul? I think?
Yeah, it was Paul, if I remember right.
Yeah.
I'm trying to find it.
That would be a very interesting finding, because all of the models that we have now
Let me just
from
put that up on the screen so that we can see what we're
Here we
talking
go. From direct observations, distance ladder, and so forth, and as well as the cosmic microwave background, everything points to a fairly zero curvature of space. So if that is variant somewhere in deep space, I would want to, make sure we're looking at peer-reviewed research, and it could be a very interesting finding.
Yeah, could well be. Could well be. Okay, there's another question coming from Ryan. Thank you for that, Ryan. Is it possible that the black hole is on the sky above our Earth, but not on others' sky? Well, what you have to remember, Ryan, is that the closest black hole to the Earth is about 1,500 light years away, if I remember rightly. So any planet within viewing distance of that is going to be able to see the black hole. And so, black holes are extremely far away and can be seen from many, many, many stars. Obviously, you will get to a point too far away where you might not be able to observe it. But no, if we can see a black hole, then it's visible from lots of other stars as well. So there we are. Paul says, to follow that up, the curvature they measured was very low. I'll try and find it and let you know by next week. Yes, I will research. Thank you for that, Paul. If you could, be really interested to hear about that. So thank you for that. Now, before we go any further, the star that we talked about earlier, this pristine star that was in the news, Daz, you're absolutely right. It's a big star. It's got 29 solar masses. So it's
Right, okay then. So it is a big star, but not the
huge
biggest.
star. Yeah. So
Yeah, it's not a behemoth. I mean, if I get a chance later on to do the other presentation, we'll be talking about the size of stars. So
Yeah.
in the population 3 stars, which are the first stars. So we'll
definitely.
see. We'll see how we get on.
Yeah, definitely.
Yeah.
Okay, right. So that's the cosmic web. That's the basic architecture of the universe, if you like. We're now going to move down to smaller things, and that is to say galaxy clusters and superclusters. And I'm going to hand you over to Roger for that one, if you're ready, Roger.
Right.
Well, we appear to have something on the sound.
Yes.
Yeah. Okay. All right. Great. So let me just put that up. I can't see your presentation there, Roger.
Oh.
Hmm.
What? Oh.
Yeah. That's interesting. Okay. Well, while Roger's trying to sort that out, got a slight problem there, which I'm sure he will fix. While we're doing that, don't forget that tomorrow night on the Space Oddities channel, we will be re-showing the item from last week where we told you the science behind Comet 3i Atlas. And that's live on the channel at 8 p.m. UK tomorrow. So it'll just be a normal video, but it will be live. So there will be a chat window there. So if you want to see it again, and if you didn't see it last week, then it will be there. Still can't see it, Rog.
Hang on.
Right. Okay.
Anything?
No.
Oh.
Oh, hang on.
What did you say?
I think we
Just
may.
popped up. Just popped up.
There we are. Oh, that's not the slideshow. You can run the slideshow from there, of course.
Why is it not?
No.
Careful. Hang on. Let me.
The perils of
Can't get the staff.
You can't get the staff. No.
Right.
So
I think we're the only ones brave enough to do live astronomy each week.
Yeah, do bear with us.
Brilliant.
Viewers, we have a slight problem. Right, let's try again.
Right, yes, that looks like the right one. That's it, right?
That's got it. Thank you for your forbearance, viewers. Right, Roger, tell us all about clusters and superclusters then.
Right. Okay. So we've been seeing the prelude here, and we're on stage. How do I get on to do the next? Right. Have I moved my slide on?
Yep.
All right. So
Yeah.
we're going from galaxies to superclusters. So we've got a matter of going from individual galaxies to the clusters, and then on to superclusters. So we're working our way from the Milky Way through our local group to a Virgo supercluster and the Laniakea supercluster, which I thought was in Hawaii, wasn't it? So it's a bit like the Russian dolls, where they go one inside of the other up to a grander and much grander scale. So that's a little analogy on what we're doing there. So we're going anything from 10 to 10,000 galaxies in a cluster. So it's the galaxies with the hot gas and the dark matter that help compose up these superclusters and galaxy clusters, and they can go out to millions of light years across. Now the picture on the left does relate to the Coma cluster, which is roughly 10,000 galaxies and 16 million light years across. So there we go. But this is only a galaxy cluster. So they do get bigger than that, as we will see. So we can go from up to 10 million superclusters estimated in the observable universe. So just when you thought there was one, there's 10 million of them. And they spread anything at 100 to 200 million light years in their spannings. So we can they're not gravitationally bound as a whole, and they are expanding as the universe does. So everything just gets bigger and bigger, doesn't it? And another one of these is a supercluster, is the Laniakea, and that was located in 2014, spans 500 million light years across, and contains the Virgo cluster, the local group, and countless other structures, as we can see in this illustration. So it goes all the way through from the northern and southern hemisphere constellations that we can look at the night sky, and we can see they go out to 3,600 megaparsecs. So it's absolutely huge, ginormous, and the Laniakea represents it's Hawaiian for immense heaven. I think they got that. I think they slightly underestimated the size of that, but they have got. It is absolutely immense.
Yeah.
Yes, and then we've got the most massive superclusters, the Inasto supercluster, which was discovered only 2 years ago, and that's 360 million years in size, and 2.6 to the 10th to the 16th solar masses.
Blimey.
Oh, I know.
Shut the front door.
Yeah, you'll need a few biros to write that one out.
Yeah.
And then the other one is the King Ghidorah supercluster. Now, King Ghidorah is named after the three-headed monster. So there we go. Yeah, there we go. And it was the previous record holder of only 10 to the 16th solar masses. So there we are. Bit of a weakling here. But the picture on the right just gives you some insights on the images around, which is part of what the supercluster is made up from. So when you start looking into it, you just keep. It's just like the deep sky image field that Hubble and HST managed to look at, and just keeps finding more and more of all these galaxies all clustering up to make this one huge group. Absolutely huge. But as Daz had already said, we've also got the Sloan Great Wall, which is slightly bigger than the Chinese Great Wall. And that's 1.4 billion light years long, one of the largest structures ever observed. And we've got enormous empty regions of filament where few galaxies exist. And the web shows
Can you see it from
how
space?
galaxies. Wow.
Can you see?
I don't know.
Can you see your wall from space?
Yeah. Yeah. So there we go. So it's all quite interesting. So we've got projects like the Sloan Digital Sky Survey. So it's going to be mapping millions of galaxies across the vast cosmic distances. The WHL cluster catalogue identifies 662 superclusters between redshifts 0.05 and 0.42. My goodness, that's a bit of a speed difference.
Yeah.
And then we've got advanced models have been revealing how the superclusters influence cluster growth and galactic dynamics. So as we allow detail to come up with more precision through more modern technology, so we can obviously hope to find more and how they form. So superclusters preserve information about the conditions billions of years ago, and they can reveal how matter organized itself from the Big Bang to today. And the galaxy orientation rotation patterns may reveal primordial cosmic conditions. So everything's all getting to be going back to the early known stages of the universe. So let's see what will happen and what will be at the end as well. So we've interesting fact here. 10% of the universe's volume is occupied by superclusters, and 90% is mostly empty space. So dear.
Wow.
But whether the expansion will change those figures around, we yet to see. So it'd be interesting to see on how the development of modern technology will be able to see what goes on into the future. And that's what I have for tonight.
Thank you very much, Roger. Fantastic.
Thank you.
Outstanding.
Yeah. By the way, I've just put that figure in the chat. So 2.6 times 10 to the 16 is, as Barry says, thank you, Barry, 26 quadrillion solar masses. So that's a lot of mass. A lot of mass.
That is.
Yeah.
It's a big baby.
Yeah.
So, a big puppy.
Yeah, absolutely. So now we've set the scene. We've talked about the basic scaffolding of the universe. That's the cosmic web. We've now talked about the hierarchy of the objects at the intersection of the filaments, i.e. the galaxies forming clusters and superclusters. Now I'd like to talk about this mysterious force which is pulling whole clusters of galaxies through space in one direction. And just give me 1 second and I will absolutely show you the name of this thing, which is called the Great Attractor. Now you have to say it.
I thought you were going to say it was the Amazon Black Friday sale. That's been that's the biggest force I know. Okay. Sorry.
So,
the biggest draw. Yeah.
I'm going away now. Goodbye.
Yeah. So you have to say that as 2 words, otherwise it comes out as Great Attractor, which is about farming. So it is the Great Attractor. Before we go any further, just let me put Paul's comment up. If there is dark matter in voids, we wouldn't be able to tell, would we, since we only observe dark matter indirectly and there's nothing in voids for it to act on. Very true, Paul. Absolutely. We wouldn't be able to tell. But who knows?
Except for gravitational lensing.
Except for gravitational lensing, indeed. That's the only way we could detect it. So there we are. Thank you for that, Paul. Okay, so the Great Attractor is the name given to this mysterious force that is pulling the whole clusters of galaxies through space. So let's ask the question, well, what is it? It is an enormous concentration of mass exerting gravitational influence across hundreds of millions of light years. And that is obviously a huge gravitational force. It's pulling our local group of galaxies and thousands of others towards it at extraordinary speeds. And we can't see it. That's the whole problem. We can't look at it directly for reasons we will come to. But we know that it has this enormous effect on the motions of countless galaxies. Where is it? Well, it's located towards the constellation of Norma, which you may know is a southern constellation. It's 220 million light years away. It's right in the center of the Laniakea Supercluster that Roger was talking about. So that's where we're being pulled towards. The problem, as I said, we can't see it because it's hidden in the so-called zone of avoidance. Now, what on earth is the zone of avoidance? Well, if you look at, put the sun on the galaxy, as in this illustration, if you look at 90 and 270 degrees, we can look out through the galaxy quite easily. But if we look at the 0 degree mark, which is roughly where the Great Attractor is, we're looking through immense concentrations of stars and gas. And there's about 20% of the universe that we actually can't see because it's blocked from view by everything in the galaxy in that direction. So it's a bit frustrating that we can't actually see it directly, because we've got all this dust and gas and stars, everything that are completely blocking our view. Billions of stars in the foreground, and we just can't look out of the galaxy that way. And this is known as the zone of avoidance. But we can see it, if not in visible light. We can see it through radio, infrared, and X-ray. We can peer through the veil using those wavelengths. So it's not like we can't detect it at all. We just can't see it optically. So what does it actually do? Well, as we said, it exerts force on surrounding galaxies through sheer mass concentration. It influences the velocity of galaxies across millions of light years, and it creates coherent motion patterns in the cosmic web. So it's a sort of a flow, if you like, with everything flowing through the cosmic web in the direction of the Laniakea Supercluster. We're moving towards the Great Attractor at about 600 kilometers per second. This is our galaxy, the local group, and others. But this is not even the biggest gravitational pull. That in itself is being pulled towards what Roger mentioned, the Shapley Supercluster. But a gravitational force that is pulling us and thousands of other galaxies in that direction is quite incomprehensible for how strong that gravitational pull is. If you think 600 kilometers a second, it's quite immense. How do we know it's there? Well, of course, the universe is expanding, but the galaxies don't move just because the universe is expanding. They all have what are called peculiar velocities. Peculiar as in distinctive, not as in strange. This is additional motion caused by gravitational attraction. So if you measure the redshift of the galaxies as they're moving and compare that towards what you might expect to see, astronomers detected this massive gravitational pull. 600 kilometers a second towards the Great Attractor. 1,000+ galaxies have been measured to map this gravitational flow. So, you know, a good fair-sized sample of galaxies, 1,000+, to detect this gravitational flow. And it's 220 million light years away. A very brief discovery history. In the 1970s was the first time that astronomers noticed these unexpected galactic motions inconsistent with the Hubble flow from the what you might expect from the expansion of the universe. 7 astronomers who became known as the 7 Samurai, they published definitive evidence of this in 1986, and then from then on advanced surveys mapped the surrounding structures revealing complexity beyond the initial models of the Great Attractor. And as Roger said, in 2014, finally the Laniakea Supercluster was identified, and the Great Attractor lies at its gravitational center. But it's not as simple as the mass in the center of the Laniakea Supercluster pulling us. There's slightly more to it than that. So the question is then, is there only one Great Attractor? Well, no, because there are multiple mass concentrations influencing galactic motion. The Shapley Supercluster, 650 million light years, and that's pulling Laniakea itself. As we said, it's got this 26 quadrillion solar mass, and we've got the Norma Cluster. It's a significant galaxy cluster, partially responsible for the Great Attractor's gravitational signature, and there are other attractors as well. If you think of them as sort of being over densities in the cosmic web, regions of the web that are more dense than others. And of course, these all do shape local galactic flows. So what does the Great Attractor affect? Well, it affects our local group, the Milky Way, Andromeda, and nearby dwarf galaxies, the Virgo Supercluster members that Roger talks about, thousands of galaxies across hundreds of millions of light years. And of course, as we said, the overall structure and dynamics of the Laniakea Supercluster are also affected. But what it doesn't affect are distant superclusters beyond its gravitational reach. Solar system's dynamic, because it's far too distant to have any effect on the solar system, or indeed anything on the Earth. So as far as we're concerned on the Earth, doesn't make any difference to us. But the fact that you've got these incredible gravitational flows that that are not due to the expansion of the universe is quite amazing. And the Great Attractor does shape large-scale structure, but at greater distances, of course, the expansion of the universe overcomes everything and dominates at far greater distances. So is it possible that we'll ever reach the Great Attractor? Well, no, because the acceleration of the expansion of the universe due to dark energy will overwhelm everything eventually, and cosmic expansion will always win. So we're never going to reach the Great Attractor. And in fact, it's been discovered that we're already slowing down because of the expansion of the universe is beginning to counter the gravitational effects of the Great Attractor. So expansion wins, basically. And even if we could reach it, the journey would take billions of years, longer than the Milky Way's remaining lifespan before merging with Andromeda. Can we see it? Well, we can see it with infrared breakthroughs, penetrating all that dust to reveal hidden galaxies. Radio astronomy mapping the hydrogen gas distribution behind the galactic plane, the bit that we can't see in the zone of avoidance, and X-ray surveys detecting the hot gas in massive galaxy clusters. So what is the Great Attractor? Well, there are some leading theories. We've already said that it's a gravitational pull from the center of the Laniakea Supercluster, which in turn is being pulled by the Shapley Supercluster. It's a concentration of multiple galaxy clusters, including the Norma Cluster, and that creates an extraordinary combined mass. It's an exceptional accumulation of dark matter over density, providing this gravitational scaffold. So it's a dense area of dark matter, and it's the intersection point of multiple filaments in the large-scale structure. So as Daz was saying, the cosmic web is very important in all of this, because if you think of the filaments and the nodes, where these filaments intersect, you get these enormous gravitational structures that are just sort of yanking galaxies along. So what isn't it? Well, it's not a single object like a black hole or other exotic phenomenon. It's a region of significant mass concentration, likely composed of ordinary and dark matter in galaxy clusters, whose collective gravity shapes the motion of our cosmic neighborhood. So there you are. So that is the lowdown on the Great Attractor. Team, got any comments about that? Viewers, got any comments? No. Okay.
Well,
Yeah, well, that's
makes sense.
sorry.
What's up? No, it makes sense that there are local concentrations of matter and dark matter that reach out, far beyond their local space and are able to curve space enough that it affects distant galaxies. And as far as our solar system, because they're so far away, the gravity of our sun, the gravity of our Earth is so much greater. So no problem, as I think you mentioned.
Yeah.
But, it doesn't seem surprising to me.
No.
Yeah, because even the Shapley supercluster, that's moving in a direction, and it's also dragging us behind it. Which means, as you said, we're being attracted to it, to the Great Attractor, and to towards the Shapley. So where is this all going to end? Where are we going to end up? It does seem it's a fascinating, theorizing what's going to happen, as we said. But the thing is, unfortunately, the Milky Way galaxies got a sell-by date, so possibly it won't be the Milky Way galaxy as such when all this starts to really kick off.
No.
So
absolutely. And I think, we're so used to thinking of our own galaxies being something vast, 100,000 light years across, and for us that's an incredibly vast structure. But when you look at the Milky Way in the grand scheme of things, how tiny it is, and how we are part of a local group and a local cluster and a local supercluster,
exactly,
makes us feel incredibly tiny, and it makes you realize what a totally insignificant speck.
It's basically how many supers you can get in front of the massive cluster bit. So because they're obviously going to get bigger and bigger and bigger. So and of course they're all, because they're so big, they got the gravitational pull. So where are things going to go if they go that way? So
exactly. It's just the scale of all this is just incomprehensible to us. Our brains are not built to deal with these concepts of size and distance and mass and everything else. But we do try. It's not our fault.
Yeah. So, the thing is, what makes me snigger is that as you talk about the zone of avoidance, that sounds very dramatic. But then also, as we said, we're all moving in certain directions, and it's also got the name of dark flow.
Yes, dark flow.
So which is, if you remember, if you got this, if it's got the word dark or similarity, then it basically means we don't know. No. We're not sure what's actually going on, but of course we know we're being attracted. All of this is being controlled by, as you said, dark matter, and gravitational pulls, and they're all going in different directions. Because some people turn around and say, well, if the universe is expanding, because you were talking about the Andromeda galaxy, they say, how come the Andromeda galaxy is coming towards us?
Yeah.
Well, it doesn't mean that the other galaxies can't be attracted to other galaxies and move in directions. But when you talk about groups, we're talking about the whole group moving in one direction towards a bigger group, to a super group, and onwards. So this is it's hard to imagine, but this is all going on, and at such a rate of speed that we don't feel it.
No, that's right. Yeah. I remember a couple of years ago, dark flow was very much a buzzword in astronomy.
Yeah, I can remember when it all came back.
Lots and lots of articles and things written about dark flow, but all it is gravity. Gravity is the architect of the universe, and that's all it is. It's just Newtonian physics doing its thing, basically, isn't it? So
if you remember a few years back, it was dark matter, dark energy, and dark flow. They were the three, and then of course then you chuck singularities on the top as well. So
So when you look at it, Daz, just during my lifetime, how things have come on. For example, I remember attending a lecture by Heather Cooper in London back in the 80s, where she was putting forward the tentative possibility that our galaxy may have a supermassive black hole at the center of it, when it was pure speculation. And there were a lot of people in the audience who definitely didn't agree with her. There were quite some heated discussions about it. And now, of course, we know it, it's definitely there. We have an image of it.
we have an image of it. Here we got a photograph of it.
Yeah.
I remember attending the same lecture with the same person. Not the same
Really?
not the same time probably, but it's not in London.
Oh, right.
I remember attending the
Yeah,
lecture.
because everything's got to start as a theory.
Yeah.
And then
everything's got to start as a hypothesis.
Well, hypothesis.
And if it's
and
lucky,
then
it gets promoted to a theory.
yeah, then of course then you got to then develop the methods to prove it. And these of course these methods have got to be able to be replicated and the results replicated, and it's called the scientific method.
Yeah,
which is
there you go.
how these things work, and you've got to be prepared to change your mind.
Yeah, absolutely. But people are just generally sometimes not willing to change their minds about anything. I had quite a heated discussion with a guy on Facebook this week who categorically denied that black holes exist. And so I just posted in the images of M87 and SAG A star. And of course, he came back with a predictable, oh, that's just CGI. I mean, what can you do with these people? Anyway, so Ian says, with observation, surely. Yes. So I guess you can say that. But in terms of ideas about what you're looking at, it starts with a hypothesis. So there we are. Sandra says, I liked Heather Cooper. So did I. I was lucky enough to meet Heather several times when I used to go to Astro Camp in the Ashdown Forest in Sussex back in the day. And she and Nigel Hembest used to brew their own wine, which they called, as an amalgamation of their name, Chateau Hencoop.
Yeah.
And
it was absolutely lethal stuff.
I mean, the only thing I'll say with Ian is that when we would talk about, I mean, everything that we talked about, say with the Big Bang, the start of the universe, a lot of that was it started, like I say, with a hypothesis. So they didn't actually start from really observations, and then these hypotheses and theories have been developed with using observations. And again, as if you remember when I was talking last week about the first stars and how we saw them, and how we thought that they were growing and how they formed. And again, I'll be talking about that hopefully a little bit later. They all started hypothetically, so they didn't. But it's the observations that now that we're seeing with the Webb are proving or disproving or making us think yet again about the early universe. So yes, it swings and roundabouts. I mean, sometimes we might see something that's odd and say, "Well, how does that work?"
Exactly.
And you if you think back to the ancient astronomers, how they try to explain retrograde motion with using wheels within wheels and things like that. It's how you a method, and at the time it was valid because that's what they thought. But of course, with observations and more observations, more theories, more things being proved and disproved, we now know that the sun is the center of our solar system. Not the solar system doesn't revolve around the Earth. So
absolutely.
It's very interesting. The history of how things develop is very interesting. Cosmology and all that. So yeah.
Absolutely. By the way, apologies from Lou. He was in a room at the university, and somebody else wanted to use it, so he's had to
Don't they know
leave it.
who he is?
Yeah. So yeah, exactly. Don't they know space oddity, for God's
Yes.
sake?
Gosh.
So there we are. So apologies from
Do
Lou.
you know who I am?
Yeah. Who are you? Yeah. Okay. Yes, Catholic priest Georges Lemaitre was a good example of that, of course.
Yeah.
Yes, and he had the right idea, but of course wasn't taken seriously, and he was, intensely worried about his theories. So about the Big Bang, but there we are. And Ian says we don't just hold on to a theory for dear life, though. Well, of course not.
Oh,
Theories.
Talk to Fred
theories
Hoyle
are
about that
modified.
in the steady state.
Yeah.
He took that to his grave.
Yeah, absolutely. So yeah, I mean, theories are there to be modified, and theories are never proven. Of course, they are correct at the time, but of course, a good scientific theory can be modified in the light of future observations, or discarded altogether. So, but they're the best we've got. Yes, Big Bang coined as a joke. Yes, Fred Hoyle on BBC Radio.
BBC,
in
on an interview.
1962, I think it was.
I mean, he was the biggest detractor from the Big Bang, saying it didn't exist. But he used the word Big Bang, and all of a sudden, he gave it the name. How ironic is that?
Yeah. He used the term Big Bang to mock the idea, and it stuck. But he never rescinded. He never gave up his belief in steady state theory, even until death. But it's a shame that he is largely remembered for that.
Yeah.
Because if you say to a lot of people who know about astronomy, Fred Hoyle, they'll say, "Oh, a steady state." But Fred Hoyle was the man who told us how stars work.
Yeah, stellar photosynthesis, nuclear.
Stellar photosynthesis, green stars.
How the star grows from the sun of another star.
Yeah, there we are.
Sorry.
Okay, so anyway, enough chat. So let's move on now. We're going to go up to Roger quite predictably, and Roger's going to tell us what's in the night sky, and then of course after that we have the viewers gallery for the week. So Roger, what's up in the night sky? Apparently nothing. Roger, can you hear us?
Can you hear us? We can't hear you, Roger.
Can't hear you, Roger.
I was on mute. Oh,
God. You can't get the staff, really, honestly.
No.
We're professional, though.
Anyway, so we're currently experiencing a new moon tonight. And if the sky is clear and you look out towards the northwest, you might find a comet. Spoiler alert. Anyway, so we're working our way through to the first quarter through the next week. So not too much of an influence on the night sky with the lunar glow of the night sky. So that's all well and good. And looking out towards the southern horizons, we can see the setting of the winter triangle, or the summer triangle even. And if we look over towards the northwest, we can see in this illustration where Comet Lemon is. And I'll show more precise location later on. But
there's been some lovely images of Comet Lemon.
Absolutely.
Beautiful.
Yeah, so we should be able to use just an ordinary camera, really, and perhaps a short telephoto lens will be able to get some of the detail and the sky of the tail as well. So maybe we might be able to get a picture of the comet in the gallery next week. But we have got Saturn still in the sky quite nicely, as we do with the Andromeda Galaxy, which will almost get overhead as the night progresses. So that's all well and good. And we've also got some of the winter constellations coming up through, which is a good sign, especially as next weekend the clocks go back an hour.
Do they go?
I know. But during the early part of the night and latter parts, we will see Jupiter coming up through. That's in Gemini, down below Castor and Pollux. And soon before dawn, we've also got Venus coming up through. So some nice bright objects in the sky there. Okay, so we've got some meteor showers coming up. In fact, we've got one peaking this very evening, the Orionids. So we've got up to 20 meteors an hour, and that's from the comet Tully. So streaking through at 41 miles per second. So a little bit slower than some of these galaxies and super galaxy clusters, but there we go. So any looking up at the night sky, you might be able to find a comet and also some meteors. And I have seen a picture of a meteor quite close to the comet on one of the social media pictures. So that's quite good.
Oh, I saw that one.
Yeah.
Brilliant.
So very good. So we'll be coming out from the radiant of Betelgeuse. Don't say it 3 times. And so that'll be in the southeast, looking really to get a proper view of it, or in the northeast in the southern hemisphere. Well, that won't apply to any of the viewers here. So as I said, we've got Comet Swan, which is traversing through Aquila, and if you look down below between Altair and the horizon, you might be able to spot it as soon as it gets dark. So have a look for that. And as you can see, between the today and the middle of November, it's really zooming right across. So it'll be heading over towards Andromeda and Pegasus, and well, through Cetus, but they'll be below the square of Pegasus as well. So quite a possible opportunity there. It's not too bright, but obviously with binoculars and some equipment, photographic equipment, you will be able to pick it up. And fortunately, it is slowly dimming towards the middle part of November. So it goes from 7.4 down to 9.6. But that's how the cookie crumbles. But also we've got Comet Lemon, and that's coming through Boötes at the moment. So we can have a look through Boötes. If you, north of Arcturus, you might see it, and it is a lot brighter. It's getting quite bright now. It's about at its opposition, I believe. This it might have been yesterday. Let me just have a look. But obviously trailing down towards down through Hercules. So it will become quite a good object to photograph, as many people have managed to do so. And as you can see, it's trying to brighten up to about just under magnitude 5 over the next fortnight or so. So it will become an interesting object, although for us, it might get a bit too low by the time it gets darker to see to cross to, but take the opportunity to see what we can. So planetary highlights. So we've got Mercury and Mars conjunction between the 19th and the 23rd. So they will become up to 2 degrees 2 days ago. So it will be quite close together. So if you've not seen Mercury before, it's a good opportunity to get that. Sandra's asked, why is it called Lemon? Because the Lemon Observatory was the first one to record its position in the night sky. So that's that hopefully answered for Sandra. And Mercury will reach its greatest elongation on October the 29th. So it'll be the highest point above the horizon. So good opportunity to spot that little planet on the horizon. So what else have we got to come? We've got Andromeda, which will be almost overhead in the earlier, well, around this sort of time. So it's quite an interesting patch of blurry fuzziness through a pair of binoculars, if anyone has not really seen it. And if you can see it in a dark enough sky, it will become visible. So have a look at that. Right, we have a gallery Not quite as big as we had last week, but we still have our regular contributors. And the first one is from Michael Murphy, and he's got a image of Comet R2 Swan. And he's got done it with a kit lens and an 1100D camera. So it's 9/32 exposure. So he's over on the left-hand side of all the different objects and stuff that we have got. And he's got it right in the center. It's a very tiny little green fuzzy blob.
Well done, Michael.
So
captured that.
You did. It's quite an interesting wide-angle field view to show it. So well done for doing that and getting the all the objects that are in the field of view labelled as well. So well done. Okay, so we've got some from Sandra. Now this is with her C-Star S30, and it's the Bubble Nebula.
Ah,
and there we are.
Oh wow. That's pretty good for a C30, isn't it?
Absolutely.
Nice little cluster at the 7 o'clock as well. Nice.
Yes.
Yeah.
Oh, well done. And another little bit,
and
a bit of the nebula up in the top left-hand corner as well.
Yeah.
Yeah.
So for quite a short experience, exposures, it's
probably experience as well.
Yeah, I mean, Sandra's not that far away from me, so I wonder if she got clear skies and I didn't. I'm going to write to my MP.
Yeah, absolutely. And not only did she do that, she did the Pac-Man Nebula as well, and that's 51 minutes altogether.
Oh, that's nice.
Oh, that's lovely.
Oh, that's nice one. Yes.
Well done.
That's beautiful, Sandra. Well done.
Yes.
Just a question for Sandra, if she can pop it in the chat. Are you using it equatorial, or are you just letting it track itself, Sandra? Just as a matter of interest.
Right.
Lovely.
Right. Now we've got a couple from Lou when he was in Iceland. So we've got a lovely, beautiful sunset from Hoffen.
Oh, that's stunning.
Oh, lovely.
I love that photo. It's beautiful.
Lovely colour. Very nice. And he also did one at high noon, but without Clint Eastwood.
Just don't deceive me, oh my darling. That's lovely.
Got an interesting view.
That was Gary Cooper, not Clint Eastwood.
Yeah. I mean, also, can you see the green comet?
Yeah. Don't be mean. I don't know
if Leyland's spaceship from 3 Eye Atlas.
Yeah, put that on online, and people are going mad for it.
Absolutely.
Yeah, absolutely.
Hopefully, that might be one of the better roads that Lou was on, because that doesn't look too potholey.
Yeah, it looks like tarmac,
right?
Doesn't it?
And we've got one from Jerry inside the Sol Nebula, also with a C-Star S30. Oh,
lovely.
And we've got this.
Oh, wow. That's amazing.
Yeah.
Look at the detail up in the top right-hand corner. That's lovely. That's fantastic.
He did all right there, didn't he? And he's done. Oh.
There we are. Sandra says tracking itself, but on a tall tripod with a ball mount. I'm going to purchase a different setup so I can do it equatorial.
Oh, right. I just wanted to know, just being nosy.
Yeah. Okay. And that's what we have from this week's gallery.
Thank you very much, Roger. That's fantastic. So, as always, viewers, we would love to have your images in the gallery. Especially if you get any of either Comet Swan or Comet Lemon, we'd love to see your comet images.
Yep.
And you can send them to us, as usual, by attaching them to an email, 1 image per email, please, and addressing it to gallery@spaceoddities.space. Gallery@spaceoddities.space.
I mean, that was an interesting question that Sandra asked, why was it called Lemon? If you notice that most of these comets have all got the same sort of names, and it is because of these mass surveys done by observatories. It's almost done professionally now, just to comet hunt. But the best way for any amateur astronomer to find a comet is usually at dawn or at dusk, looking towards the east or west, whichever, and try and pick one up as the sun's coming up or going down, because the big observatories stay away from there because there's too much light coming up. And if you find it, remember, you get to name it.
Yay!
Yeah. As I put in the chat, the Lemon Observatory is situated on Mount Lemon in Arizona. So that's where it comes from. The Mount Lemon Sky Center. It's part of the University of Arizona, the observatory. So just thought I'd tell you that. Derek says, great images again. Well done, all. Yes, indeed. And don't forget, if you submit an image to the gallery, you get your own little gallery on the Space Oddities website, which, as always, is https://spaceoddities.space. And you have your own galaxy there, so you can thrill your family, friends, and neighbors.
You get your own galaxy.
Yeah,
get your own galaxy.
Oh,
Yeah.
not a gallery, you get a galaxy.
And they're all up this week. All this week's images already up on the website.
So you get some chocolates as well.
Yeah, absolutely. Sandra says, yes, it used to be names of people who discovered it. It still is, Sandra. If you're an individual and you discover a comet, you still get it named after you. But you also get it named after you if you're a satellite as well. Because, for example, the famous comet of 1983, IRAS Alcock-Araki, or Araki-Alcock, I never remember which way it goes. The IRAS in that was the Infrared Astronomical Society, which co-discovered the comet, along with Mr. Araki and Mr. Alcock. So it had 3 names attached to it as discoverers. So there we are. Okay, well, we'll look forward to another galaxy. Keep the images coming in. We absolutely adore looking at them, and we love giving you your own galaxy on the website. So there. So what we're going to do now? How are we doing for time? Right. So what we're going to do now is go back to Daz, and Daz is going to tell us.
Okay, then let me just set this up.
Yeah. Daz is going to tell us a bit about the JWST and the early universe and what the JWST has been discovering. So there we are.
Just okay then. Can you see the full picture?
Yep.
Okay then. Right. So what we're looking at, as you remember last week, I was talking about. We were talking about the beginning of the universe, and with the new stars and everything. And we said that basically the James Webb was basically revolutionizing what we are actually seeing, as well as trying to help us to confirm or deny our observations. We were basically seeing things that really just didn't really make sense. So what we've got here is basically the James Webb unveiling the dawn of the universe, and it's how the most powerful telescope ever built is rewriting our cosmic origins. Now, this is what some of the images that the James Webb was seeing, and what we got is within the first 500 million years after the Big Bang, Webb discovered galaxies that shouldn't exist according to the standard cosmological models. These galaxies appear remarkably massive, some containing billions of stars, at a time when the universe was supposedly still in its infancy. So we were seeing these mature galaxies, you can see here, very faint, but all red because of the redshift and the fact that they've been traveling all these billions of years. Theoretical models predicted small primitive structures slowly assembling over billions of years. Instead, Webb revealed mature, massive galaxies with well-developed structures appearing astonishingly early in the cosmic universe. Now, what we also found is, of course, as I said, when they started to look at these little red dots and that, they believed that they were galaxies. So what they did, so if I just read what we've got here, so this is the actual images that they were looking at, and they started to look at, and they believed because they were so bright and we could see them, they were galaxies. So it says when the James Webb Telescope started scientific operations in July 2022, we immediately saw the early universe was full of perplexing populations of cosmic objects that we had never seen before. Faint little red objects at extreme distances, whose, due to the expansion of the universe, had their wavelength stretched to turn them red. Sorry, I didn't mean to do that. Let's go back. To turn them red. These numerous objects were dubbed little red dots. Well, that's obvious, wasn't it? LRDs. Initial studies showed these objects to be compact, roughly 2% or less there than the diameter of our Milky Way. So these objects were really big and fully formed within the first billion years after the Big Bang. At first, astronomers believed they could be young, dust-shrouded galaxies forming stars at an amazing rate, and that is where the fun began. It did not fit the current models of star and galaxy formation rates for the early universe. Secondly, using ALMA, this is the second time been mentioned today, the Atacama Large Millimeter Submillimeter Array in Chile, they searched for signature of the dust shrouding these early galaxies in millimeter wavelengths, but they saw nothing. The conclusion was undeniable. No millimeter radio emission, there's no dust. This also challenged the idea our LRDs could be galaxies of any kind because they are built around a supermassive black hole. So basically, we should have been seeing, uh, when we looked at this using ALMA, we should have been able to look in millimeter radio emissions. We should have been able to detect the dust, but they found none. And of course, if you haven't got dust, then there can't be a galaxy there. And of course, a galaxy would also be powered by a black hole. As we know, the galaxy pulls itself towards the together, and some of the dust and gas falls into the black hole, creating an active galaxy nucleus that emits extremely bright X-rays. But again, astronomers failed to find a hint of such emissions, so there were no X-rays in these little red dots, the LRDs. So what were these LRDs? Stand up Devash Nandel from the University of Virginia. While studying for a PhD in Switzerland, in Geneva, Switzerland, he became fascinated by the question, how large can a star become? When we talk about stars, we have some clear demarcations about size. A sun-like star is close to 1 solar mass. High mass stars start around 7 solar masses to about 1 to 120 solar masses. So the one Andy was talking about earlier on was sort of towards the bottom end. So although that is still a massive star, trust me. And Andel believed the early conditions in the early universe were so different than today that it allowed the first stars, aka population 3 stars, to grow even bigger. These supermassive stars had never been seen, but theoretically they could exist, possibly containing about 100th or even 1/10 of the mass of a small galaxy. Now that's a lot of mass. There's a lot of mass in there. These supermassive stars were beyond imagination, thousands, if not tens of thousands, the mass of our sun. And that is huge. The early universe consisted mainly of two elements, 75% hydrogen, 23 helium, and 2% other smaller elements. And the elements heavier than helium and so on, and lithium, we call them metals in sun speak. And the reason we do that is it messes with the chemists. I'm not going to go into the star formation and the life of stars, but if you can see the earlier presentation, it talks about the stellar nuclear synthesis, not photosynthesis, nuclear synthesis, where the stars produce all the elements, and the more elements you get when they die, they see the surrounding environment, and these elements help to cool the premium gas the hydrogen gas that was around at this time. The stellar so here we go. The stellar nuclear synthesis starts to create heavier elements that, on the death of the star, seed the surrounding gas clouds. These elements then cool the gas to allow smaller stars to form. So as the evolution goes on, and we get more and more stars, we get more and more elements. These elements tend to cool the gas, and then that means we can form smaller stars, like what we see today. So back to Nandel, who started to grow stars in computer simulations. It soon became apparent that it seemed there was no limit to how big a star could be using prime hydrogen. Starting with a population 3, but of a really low mass, say 2 solar masses, he just fed it gas at faster and faster rates. Today's stars are swallowing gas at a rate about 1/millionth of a solar mass per year. Researchers today seem comfortable that the population 3 stars, the very first stars, were growing at around 1,000th of a solar mass per year, because the more massive clouds there were feeding them. So that is quite, they were feeding on hell of a lot. Nandel turned the simulation up to 11. The stars were fed gas at a rate of 1,000 sun masses per year, and nothing went wrong. The stars did not explode. The simulation did not crash. The stars just got bigger and bigger, growing even up to 1 million sun masses. You imagine the size of that. Even the spectral characteristics, the wavelengths these objects would emit if they existed in reality, looked similar to what was being measured in LRDs. No millimeter radio waves and no X-rays. But there was one slight fly in the ointment. Hydrogen beta is a name given to a particular wavelength of light, which is 486.1 nanometers. It is prominent in the light from LRDs, so we see it in LRDs, and was thought to be linked to the presence of an active galactic nucleus. But the lack of X-rays and millimeter emissions, however, put paid to this. If you remember, no emissions, no millimeter emissions, there's no dust, so there can't be a galaxy. But Nandel's simulations of supermassive population 3 stars predicted that strong H beta would be seen coming from the surface layers of these huge stars, fitting the observations of LRDs. So again, it looked as though it was pointing towards that these could be these very massive stars. LRDs are not galaxies, but population 3 stars, just bigger and brighter than anyone had dared to imagine. Game over. But for one thing, to achieve the above results, the star was not just 1,000 solar masses or 10,000 times the mass of our sun, but 1,000,000 solar masses, which is gigantic. Neanderthal asked the question whether such an object really could exist. He then thought about a previously theorized object by Mitchell C. Begelman, Marta Volonteri, and Martin Rees in the mid-2000s called quasi-stars. In this scenario, the gas collapses as normal until it gains enough mass and pressure to spark nuclear fusion and becomes a supermassive star that will burn through its fuel in just a few million years and then collapse into a black hole. The huge amounts of gas enveloping the star could hide the cataclysm. The seed black hole would sit in the huge envelope of gas, which would then be hundreds, if not thousands of times more than the black hole. So what I'm saying is the envelope of gas would be thousands, hundreds, if not thousands times more massive than the black hole. And the black hole would accumulate more mass and grow, being cocooned in all this gas. And it would look that's something like a star. So as we know, when a star is feeding, the surrounding area has to eat up. The accretion disks get hot and we can see them. But of course, if it's cocooned in all this gas, it may look like a star. Oh, excuse me. Only a theory, but again, they would fit the observations seen with the LRDs, because you'll be getting the H beta from the intergalactic, black hole at the center. So could these be the population 2 stars? The jury is still out. But one thing is sure, the LRDs are not galaxies. The James Webb Space Telescope has given us a window into the very early universe. What we see is challenging our preconceived theories of what we thought we understood of these times. In fact, the James Webb has introduced us to a whole lot more mysteries and possibly new exotic objects to be unraveled. The end. So there we go.
So there we are. Thank you very much indeed, Daz. That's brilliant. Yeah, these little red dots, we talked about those a few weeks ago.
Yeah.
It does begin to look very much as if they are black holes embedded in a giant envelope of gas. But you know, as we've said before, the James Webb has got another, possibly, if all goes well and the telescope doesn't suffer any failures, the James Webb's got another 17 years of life ahead of it. And what are we going to discover in those 17 years? It's going to be quite amazing. And just before we finish for this evening, a quick word from our sponsor. This video is sponsored by PicAstro. It's like Instagram for space nerds. So thank you to Tom and PicAstro for sponsoring Space Odysseys. Much appreciated. PicAstro is a great app for astrophotographers. As it says, it's like Instagram, but for space nerds. And join the community on PicAstro because it's a thriving community. And you get to share all your wonderful images with other people at full resolution, not the downgraded, compressed resolution you see on things like Facebook and Instagram. Original quality images you can upload and join the community and share them and share your hobby of astrophotography with people. So there we are. Okay, right. Well, I think we are going to draw things to a close for this evening, which is no doubt going to please Derek, because we are within 3 minutes now of Derek's allotted lifespan for the duration of our live stream. So thank you, Derek, for being Mr. Timekeeper. Thank you for joining us this evening. Don't forget, tomorrow on the channel at 8 p.m. UK, we'll be showing again the section that we did last week about the science behind Comet 3i Atlas, giving you the science and not the nonsense. And we hope you can join us for that. It will be live, so you'll be able to post your questions and comments. If you didn't see it last week, is an opportunity to see it. If you want to see it again, join us tomorrow on Space Odysseys on the channel at 8 o'clock. So there we are. Well, I'd like to thank Roger and Michael and Daz. Michael's been very quiet tonight. Barry says, could little red dots be progenitor supermassive black holes? Yeah, very much so. Very much.
But we just haven't got the emission observations of light to support anything at the moment. It's just that, you know, because we're seeing some emissions which are the H beta, which would mean that there is a black hole, hydrogen beta, and of course, because there's no gas, we know that they're not galaxies. So basically, you know, but that could also be seen in the simulations from massive stars. It's sort of like, you know, which way do you go? Is there something that we need more observations on, and to find out exactly what's going on? So it's been a fascinating show.
And with the 17 years ahead of the Webb, hopefully, if all goes wrong, then there's plenty of time to make these observations. it would be wonderful if these could be progenitor galaxies, that galaxies will go on to form around these little red dots. But we just don't know at the moment. So there we are. Yes, we'd like to wish Michael a more speedy recovery, because he's still feeling a little bit under the weather.
Sorry about the quietness and.
Oh, he's a
Yeah,
Dalek.
he's not
He's a Dalek.
So we hope that you.
I had a couple of. I have answer a couple.
Yeah, definitely. All right then. So we will see you all next week. Not quite sure what we've got next week, but keep an eye on the channel. We will let you know. So from all of us at Space Oddities, thank you for being here. Much appreciated. And we hope to see you tomorrow night on the channel at 8 o'clock UK, as I said. But if you're not there, then be somewhere else.
Yeah.
I don't care.
Join us with your questions.
Yeah, that's right. So if there are any questions that have occurred to you about 3i Atlas since last week, you'll have a chance to ask them tomorrow, and we'll do our very best to answer. So from all of us at Space Oddities, have a fantastic week. We'll look forward to seeing you, if not tomorrow, then same time next week, Tuesday, 8 p.m. UK, here on the Space Oddities.